Hello everyone and welcome to this Treble webinar, which is entitled The Next Era of the Treble Web App. Our web app is our offering for architectural acoustics and sound system design. And today, as usual in Treble webinars, we have a packed agenda. First, my colleague Sarabeth will introduce a lot of new features that we are releasing. Second, my colleague Nick will talk about our integrations into Revit and Rhino and show the sort of associated geometry workflows there. Third, I will talk about improving acoustic absorption modeling, or sort of give a sneak peek into very exciting work that is ongoing on that front. And last but not least, Nathaniel Fletcher from AKRF will come and share some real-world case studies that he and his team have been working on. Before diving in, I want to share a few thoughts on the high-level vision of the Treble web application. It is a product that has evolved a lot over the last 2-3 years that it's been on the market, and we are working really hard on making acoustics design in the building industry and pro audio industries as seamless and easy and accurate as possible, with the ultimate vision, of course, of making the world a better sounding place. And here we have sort of grouped our work into 4 buckets, if you will. First, we're doing and have been doing a lot of work on improving simulation and analysis capabilities. Lots of exciting things coming out today, making it easier to interpret and analyze and visualize simulation results, making simulations more accurate and so on. Of course, with the ultimate goal of making it possible to create better acoustics designs. Second, on the geometrical modeling front, this has been a major topic in Treble for quite some time, where we're trying to make it as seamless as possible to go from building modeling software and complex, rich architectural models to the acoustic design work. There's great things we're showing here today, like the Rhino and Revit integrations, but also more to come. It's an ever-evolving topic. Third, on the material innovations, so as we all know, the quality of an acoustic simulation will highly depend on the quality of the input data. And we in Treble, along with some great industry partners, believe that there is some room for improvement when it comes to characterizing acoustic absorption materials and incorporating that into simulations. So we're working on really exciting things here to kind of improve material data quality and make that data easily and readily available at users' fingertips. And then last but again not least, pro audio or sound system modeling is a major topic. The web application is already now a very powerful tool for, let's say, PA system design. And we are working really hard on improving sound system modeling capabilities further, incorporating loudspeaker data into the platform, modeling advanced sound systems like line arrays and column speakers and so on. And we will have some major announcements on this in the coming months. So stay tuned for that. So that's kind of the high-level vision. I think we're basically ready to dive in and give the word over to Sarabeth to show us some of the new features that we're rolling out here today.
Hi everyone, my name is Sarabeth Mullins and I'm a Senior Simulation Specialist here at Treble. I'm going to take a few minutes to walk you through some of our newest features, which can broadly be described as quality of life features. These are improvements to the workflow that have been requested to us by our customers. So to kick things off, let's go ahead and come into this auditorium model to look at a few of our new results viewing features. So this auditorium, as you can see, is a couple hundred seats large, and it has a number of acoustic reflecting surfaces designed to help with speech intelligibility or music intelligibility. So these reflectors in the ceiling here, and of course a bit of a shell over the stage. Now, one of the features we've been asked for a lot is the ability to check where the reflections of a overhead reflector or a shell or some other device might be going into an audience area. So the very first overview that we can look at is the reflection density overview. In this view, you select a given plane. In this case, it's one of the reflectors at the back of the auditorium. And you select a source that you have already placed inside the simulation. And I should note actually that you can look at this view in either the simulation creation phase, as long as you have a receiver, or excuse me, as long as you have a source defined. You can also look at this in the results view after you have run that simulation. But in this case, we're prior to the simulation, and we're looking here at a given source. And I'm going to select the source on stage because we're interested to see how this particular reflector is bouncing early reflections into the upper seating area. So as you can see, we can choose to filter the number of reflections coming off of this plane by their reflection order. So either direct sound, first order reflections, second order reflections, or third. And you can select any surface inside the space or choose a different source inside the space in order to run the same visual inspection. The second quality of life feature is the color by absorption. And for this, we're going to zoom a little bit into the model, and you can see here that now the visual rendering has been updated to group planes and color planes based off of their absorptive properties. You can select which octave band you want to look at this at, and you can see that the color scale here is on a scale from 0 to 95, which is the range of possible random incidence absorption coefficients we support inside the Treble solvers. And finally, I think this might be our most requested feature. This is the billiard ball or particle animation view. So in this view, we allow you to look at the ray trace in animation form of a given source within a model. Now in this case, again, I have selected source 1 here on stage, and I'm going to come into the settings and make sure that I'm looking at the sphere view as opposed to one of the two-dimensional planes. And I'm going to actually slow down the automation speed so we can enjoy it a little more. In this view, we can also increase the number of particles that are being used in this simulation, and we can also change their diameter and their color coding. We can also finally add a path trace behind each ball so we can see its exact trajectory over time. Now that we've configured all of that, we can press play and see this beautiful and mesmerizing animation of the sound particles bouncing around in space. Right, so now that we've looked at those overlays, let's go ahead and look at some more features inside the results view. So I ran this simulation prior to the webinar, and we're going to go ahead and go into the reflection tracking view. If you've used the Treble web application in the past, this view should be very familiar to you. We have a plot on the left-hand side of the screen showing the direct sound arrival as well as the discrete reflections coming after it within a certain window. These are color-coded by their time of arrival, which gives you an overall sense of when the mixing time begins to form in the space. Now, if you select an individual reflection, on the right-hand side of the screen, you will see the image source path that this particular reflection originates from. And we have added new capabilities up here at the top to be able to select and filter through early reflections based off of certain criteria. So for instance, the range of SPLDB difference from the direct sound, or a range in terms of the time of arrival. However, what is more interesting is the addition of these reference curves to the analysis. So a reference curve in this case is related to academic research about the audibility and psychoacoustic features of early reflections. So we offer two different scales that you can look at, either the music scale or the speech scale. The music curve is sourced from the Auditorium Acoustics book by Michael Barron, and the speech curve is sourced from Olive and Toole's 1989 paper on the detection of reflections in typical rooms. However, in both cases, what we are seeing here is a relationship between a psychoacoustic experience, such as spatial envelopment or echo disturbance, and the reflections inside the image source model that correspond to arrivals in this time. Now, by clicking on different areas of this window, we can highlight only reflections that fall within a certain range of those reference curves. Let's move on to the second set of updates, which have to do with the placement of sources and receivers. So in previous versions of the web app, in order to add a source, you had one of two different options. You could either add them manually and include the XYZ coordinates as a part of the graphical user interface, or you could come over here and upload them from a text file. We've kept both of those abilities, but we have now added a way to add sources in bulk and a little bit more intelligently. So to demonstrate this, I'm going to show you how we offset a set of sources from a given plane inside this model. Now in this case, I want to offset it from the bottom of the rail track here, which I've selected. And as you can see, this shows up in the layer view in the offset source, which we can also use as a drop-down menu to select a different layer as well. Now I'm going to say that I want to offset this by 2 meters, but I can of course choose a different distance from the layer to use as the offset. And I'm not interested in placing only one. I actually want to place a number of sources running down this train track. So I'm going to say I want 50 sources, and I want them to be spaced 2 meters apart. Yeah, 2 meters apart. And finally, I want to create this as a group. And what that does is it allows me to transform these as a group without changing any of the spacing in between members of that specific group. It allows me to edit these much more easily. Now I'm going to add these to my simulation, and as you can see, they show up as a group here with certain group properties, such as the colors and names of the groups, which can be used for administrative purposes, as well as the ability to, for instance, apply a source directivity to all of the sources inside of this group. We can also, once we have created this group, add to it by going into multiply and saying, well, instead of spacing these on the x-axis, I want to space these on the y-axis. I want to offset another 2 meters, and I'm going to make 3 copies of this. So now we have this large array of sources, all of which have been added to the simulation, and we've just done that with a very simple click of a few buttons. The same process can be repeated inside the receivers in the creation of point receivers. As you can see in this drop-down menu here, we have the same ability, but we've also extended our ability to do surface receivers to include this as well. So we can either create from a layer, which is using that same offset that you've seen in the previous examples, or we can do the previous way of defining these grids in space directly. One of our new features as well is that we can now support a much larger number of surface receiver grid points. So that maximum value has been raised to 2,500 from our previous values. And in even more exciting news, we can now discretize our surface receivers down to 0.3 meters spacing, all of which allows you greater flexibility and greater control over the placement of surface receivers as well as point receivers and sources within the simulations. Now, one of the core features of our results view up until this point has been the ability to compare results from multiple simulations run inside the same model. This, of course, allows you to do an A/B comparison by eye of different acoustic parameters as a result of certain acoustic treatments or the use of different source placements inside the space. But we've added more ability to do a strict A/B comparison between 2 models. So we have introduced a differential view of results. So in order to demonstrate this, we're going to look at the results here, which are the results of a public address system that was run inside that train station. And in one of these cases, the ceiling of the train station is of a highly reflective material, and in another one, it has been replaced by an acoustically absorbent material. And if we click through either one of these, we can of course see that there are changes to the 220 hertz values of T20, but the extent of those differences is maybe not something we want to try to calculate by eye across every one of the grid points. So now we have this difference view. And what this does is it subtracts the value of the results in view B from the results in view A, which gives you an overall offset calculation between the two. So in this case, we are subtracting the T20 of the reverberant ceiling from the T20 of the treated ceiling to get an idea of how much of a positive impact the treatment has on reverberation time coming from the PA system. We can also, of course, select many other of our standard acoustic parameters. In this case, I'm going to look at STI. And maybe this ordering of the comparison isn't to your liking. You can, of course, rearrange these so that you are now differentiating in the other direction. While I'm on this particular topic, I should also mention that following some user reports, we have made improvements to our source summing capabilities, so that should be much more stable now than it has been in the past. Okay, and the final quality of life feature that I have to show you today is related to the view that we already saw. So similarly to the question about the ability to view the sound field as a set of particles being traced over time, we've heard you loud and clear. Many of you want to see the wave field develop over time as well. So we have gone ahead and enabled a wave field animation in the results view to allow you to look at the wave behaviors of your simulation. Now, it's important to note that there are a couple of limitations to this. First of all, you have to run a hybrid simulation or a full wave-based simulation in order to access this feature. And second of all, you need to have a surface receiver inside the simulation as well. Other than that, if you have those two requirements, there is no other setup required in order to create these animations. So as an example here, I have a small recording studio and I have created a number of surface receivers to help us visualize the wave in different planes. So in this case, I have a surface receiver parallel to this wall and parallel to the back wall, and then I have two that are parallel to the floor itself. And if I press play here, you will see the development of the wave field as it moves over space. Now this is a very busy looking visual because we have 4 different planes here. So I'm going to stop this animation and actually go ahead and remove a couple of the planes from the visualization. So if we rewind this and maybe set the speed to a little bit faster, here we can see the wave field developing over time. Now we have 2 view possibilities for this at the moment, which we would love to hear feedback on. One of them involves the addition of a small amplitude in the Z direction in order to show a general idea of where the peaks and the troughs are of the wavefront as it moves through space. But you can turn this off by unselecting the 3D view in the settings and only see it in 2D. Now, it is important to note that the 3D view, where we actually see the amplitude of the wave across this section or plane of the room, is an approximate value. This does not have any direct correlation to sound pressure levels, sound amplitude, or things like that. It's merely there to give you a visual indication of whether or not you're looking at a peak or a trough in the overall pressure wave. This, of course, is very nice to look at, but perhaps we're interested in looking at the vertical plane instead. So let's go ahead and select one of these vertical receivers instead and press play. So here again, we can see the development of the wavefront as it moves through space and time, and we can see how it's interacting with certain occluding objects inside the space. Now, I know we have a bunch of curious technical professionals watching today, so I have prepared a secondary example of this animation in a more fundamental case. So in this instance, I've gone ahead and simulated a shoebox room with a partial barrier dividing a source and a receiver, and I've defined our surface receivers across this room in such a way that we can capture the expected wave behaviors, diffracting over the upper edge of the boundary. So For all of those technical whizzes out there, here is an example of what it looks like in the most fundamental case. As you can see, as over the side, there is a diffraction above the upper edge of the boundary. There is an amplitude loss on the wrong side of the boundary, and there is a quick modal buildup in the right side of the boundary. Now, as I said before, these require surface receivers and hybrid or wave-based simulations. But other than that, these have been designed to fit seamlessly into your existing workflows so that you can prepare this sort of analysis without having to think too much about the visuals of the system. Thank you so much. I hope these features will help improve your day-to-day workflows and that you enjoy the rest of this webinar.
Hi there, my name's Nick and I'm a Senior Solutions Engineer here at Treble Technologies. And today I'll be going over two new plugins we've released, one for Rhino and for Revit, and I'll be showing a little bit about how these plugins work and how you can get your geometries from either tool into Treble seamlessly. First, let's start with our Rhino plugin. So this has a very similar functionality to what our already released SketchUp plugin does, but now we've also integrated it into the Rhino ecosystem as well. So to install the Treble plugin, all we need to do is launch the packet manager within Rhino and simply search for Treble. Once you've installed the plugin, then you can launch the plugin by typing Treble in the command window. For users that have used our SketchUp plugin before, you'll notice a very similar user interface. And what we can do now is check our geometry, but also fetch geometries directly from Treble as well. So once I've installed the plugin and I've created my geometry, which I've done here, you can see that I've made a fairly simple performance hall, and I've also assigned all my different layers here as well. I can launch the Treble plugin. Simply by just typing Treble in the command window, the plugin is now launched, and we'll notice the first thing it's asking us to do is to set up layers. So once I click that, what is required is for us to move whatever geometry that we want to be imported into Treble's default folder hierarchy, or Treble's default layer hierarchy. What that essentially means is that only the layers that are within the hierarchy will be imported into Treble. Now this can be useful because it's common to also import additional geometry or even PDF drawings within Rhino to help make the model creation a little bit easier. So instead of needing to delete these items from the model itself, we can simply just drag what we need directly into our Treble folder. So now that's been done, we can now check the geometry. Now this checking process is analyzing the model, and it's looking for if the model is watertight, and it's also looking for areas where some additional feedback or efficiencies can be made. We can see that this geometry is passed without any further updates or suggestions needed, and it's ready to be uploaded. The other functionality with our Rhino plugin is that it supports a two-way communication stream. So not only can it send models to Treble, it can also fetch them back again. So for example, if I click the fetch feature now, all my projects that have been uploaded to Treble, I can now fetch the geometries back. So for example, this auditorium, it'll ask me if I want to replace what's in my existing Treble geometry. So I'll say yes. Okay, and now I've fetched my, my auditorium here, and I can start to edit that as well. One of the useful features about our Rhino plugin is that it can fetch models from Treble that didn't originate from Rhino. So for example, if you or a colleague created a model in SketchUp, uploaded it to Treble, it can still be fetched via the Rhino plugin as well. So for example, this auditorium that we see here was also created in SketchUp and now been fetched into Rhino. This is great for being able to support a number of different workflows, particularly if teams have diverse ways of working and using a series of different CAD tools as well. What we will notice, however, is that these models have come in as meshes, and they can be a little trickier to work with. So what we would normally recommend is to select the model and then to change your mesh into a NURBS geometry. And we can do that in the command prompt with the mesh to NURB command. So just like before, we can now check our geometry to see if there's any feedback being provided by the plugin. What we can see here is that there are some notifications that we're being given. Primarily, we've got some short edges detected and some small gaps as well. And what this refers to is very small geometric detail within the model. And this can have an effect primarily on the simulation time when doing wave simulations. So if we highlight the plugin, we can also zoom in on some of where these areas are, and that can help us simplify and refine the model. Now, it should be noted that these are just recommendations. You don't have to make these sort of changes, but if you are experiencing longer simulation times, then the single most efficient thing that you can do to improve your simulation time in a wave simulation is to simplify the geometry. So, if we're happy with our edits that we've made within the Rhino plugin, we can then upload the geometry like before. It's also worth noting that we'll be leveraging the Rhino plugin in the future to make leak detection easier and to also help make approximate watertight shells of models as well. So stay tuned for some of these future updates to come. The next plugin that we've released recently was for Revit, and this is great for our BIM users. Instead of needing to create a secondary acoustic model separately in a CAD tool, you can create your Revit model and send geometry straight into Treble. The Treble plugin for Revit is a little bit different as opposed to our SketchUp and Rhino plugins, because what it also does is applies an automatic geometry simplification and space detection process. I'll go through this in a little bit more detail, but first I'll tell you how you can download the plugin. For this, you need to go to the Autodesk website and you can search for the Treble plugin there. Here you'll find our Treble plugin and you can download it that way. So now we're in Revit. I have a model here in front of me, which is a sort of a corporate office. And we can see from the outside, we've got some various features about the model. We've got the sort of terrain or the trees, as well as the building itself. And if we have a look at some of the floor plans, we can see we've got our entrance and hallway area here. We've got some workspaces on the ground floor. We've got a few different levels as well. So this is connected from the ground floor up to the second floor hallway, more offices, and we also have a basement here as well. We can also cut a section view and see a little bit more inside the building. So we can see this is the hallway we were looking at before with the staircase up to the first floor. And inside we have our reception area here with some reception desks, furniture. We can see some of the detail around the furniture as well. And yeah, a bit more about the model here too. We can see here the chairs and tables for the various rooms. And perhaps at the back here we also have a office space with our chairs and desks as well. So what the typical workflow is that would be required to create an acoustic model from a Revit project such as this would be to manually measure out and create in a separate CAD software the models from scratch, be it Rhino or SketchUp. And of course this is an extra step and it can be quite time consuming to essentially remodel everything from scratch as well. One of the problems, or I guess why this exists in the first place, is because typically Revit models are too complicated to be used as acoustic models. As we could see with some of the furniture that we were looking at before, it's too detailed to be included in an acoustic model. We've got this railing here as well that wouldn't play nicely in acoustic simulation. And because of the way that these walls are all built up as well and other parts of the model, trying to simplify it ourselves manually also takes too much time. It would be much simpler to just measure out everything and recreate it from scratch. So that's exactly what our Treble plugin is trying to do for you. So instead of doing this, we can launch the plugin here. And we're left with a few options that we can select from. We can select rooms to export. So first we would navigate to which project we would like to import these models into. We can go to next. Now we can find all the rooms that are within our Revit project here. And we can search for exactly the ones that we would like to import. So for example here, maybe I want the hallway and entrance area. and maybe I want an open workspace as well. And I can select those and then export them directly into Treble. There are also a few other options that we can use to export our rooms from. So instead of selecting rooms individually, we can also select to export the entire project. But we also have another option here, which is to export from a 3D view. So this is now looking at all the different 3D views that we have, and we can export from that instead. What's useful about this process is that you might have a very large Revit project. And what we do when we commence the simplification process is we create an IFC export of your model. Exporting via a 3D view will make sure that the IFC we create is only to the confines of that section box, which means that it can make the import process much more efficient than trying to do the whole project at once. The last option we have here is to export rooms from a 3D view. It can reduce the time it takes to export your Revit model to Treble. So we only look at the bounds of which the 3D view has been made. So for example here, I've got my 3D section 2, and if I navigate to that section here, it's just a small sample of the entire model. And I can use the plugin to export via this selected section. And now we can see, if I select my project again, that there's only a selection of the same rooms that were available before. And that will help save the time when we export to Treble. So now we've used the Revit plugin to export this whole project into Treble. So once that's been successfully completed, you'll start to see we have all our spaces over the left-hand side here. So each individual space that needs to be simulated has been broken into individual models that can now be selected. And we can see here with this entrance hallway, we've got two icons on this little box here, and it's indicating that this model is watertight, which means that a wave simulation can be performed, and geometric simulation is also available as well. So if we start to have a look into the details of this model, we can see how some of the geometry has been simplified compared to what it looked like in our source Revit model. So we can see we've still got the sofas here, but they've been simplified, as have the shelving and the desks as well. And there's also some furniture here in one of the common areas here. And again, we've got some more tables, chairs, and sofas as well. So given the size of this model or of this particular space and the complexity of it, this can save a bunch of time as opposed to needing to try to create something manually. And because it's watertight as well, there's no additional geometry preparation that needs to be done. And we can see that all the layers here, which have come through from the Revit model itself, have also been preserved so that it will be easy to assign our acoustic materials to it once we reach the model setting. We may not need to import all our models, so we can also toggle on and off our spaces up here, and we can select things individually as well. So perhaps I'd also like to select an open plan office as well. And again, we can see the level of detail that's been imported here as well. So the chairs have been simplified into 2D planes, and the tables have also been simplified and preserved as well. And we can select that one to import as well. So once we have selected the rooms that we'd like to simulate, we simply assign those to a project, or we can create a new one ourselves, and they're ready to go. So that's it. I hope you enjoyed seeing how our Rhino and Revit plugins function, and enjoy the rest of the webinar. Okay, bye for now.
Okay, the next topic on the agenda is around acoustic absorption modeling, or in other words, the material data that is used to characterize the surfaces in a room acoustic simulation. Now, as we all know, the quality of any physics simulation will highly depend on the quality of the input data that is used for the simulation. And in room acoustics, the industry standard approach has been to use the practical absorption coefficient, which is measured in a reverberation chamber. Now, that method has certain limitations, or sort of a fairly high level of uncertainty associated with it. So we in Treble, together with some great partners, have been working on this topic, where we are coming up with a way to characterize the surfaces in a more precise manner, or characterize materials and acoustic products in a more precise way, and make that data readily available to our users. Our ultimate goal is, of course, to sort of reduce this material uncertainty, or in other words, improve simulation accuracy and simulation quality, which in turn then leads to kind of improved acoustics designs and sort of more confidence or less risk in the design process. Now, we're not fully releasing this here and now today. We aim for a big release in the fall, but we wanted to share this work already now with the acoustics community, give insights into the methods we're considering, the partners we're working with, and how this will all look, for the purposes of essentially getting feedback from the acoustics community, and also to welcome if there are any additional partners that would like to work with us on this. So in the following slides, I will first briefly talk about the way this is done today, and then give insights into the methods that we are developing. And finally, I'll give the word over to Oliver, my colleague, who will show a little bit sort of how this will look in the Treble web app once we release this. Now, when it comes to the limitations of the industry standard approaches, one can mention a few things. First, from a reverb chamber measurement, one can actually get non-physical results where the absorption is more than 100% at certain frequencies. Second, the whole methodology around the absorption coefficient assumes a diffuse sound field, but reverb chambers are not able to produce perfectly diffuse sound fields, and furthermore, once we do simulations in real-world conditions, those will not be diffuse as well. Third, it has been shown that different chambers give actually very different results for the same absorber. Here's an interesting study from 2010, where the researchers took a piece of absorber and measured it in several different labs, 13 different reverb chambers. And we see here in the results that the measured absorption coefficient is, I think it's fair to say, it's quite all over the place. So there's a high level of variation here, or high material uncertainty, which will of course impact simulation accuracy downstream. In addition to this, one can mention that datasheet values are typically only reported for one or maybe two fixed ODS, overall depth of system. Furthermore, the absorption coefficient does not cover phase. It's an energy-based metric only. And finally, I'll mention that mounting conditions have also been shown to affect the resulting measurements from a reverb chamber. So I would say, in summary, the practical absorption coefficient has a pretty high level of uncertainty. There's variability between labs of where it's measured, and it is sort of a proxy measure of the material, not an intrinsic or deterministic property of the material itself. So we argue that the industry deserves higher quality data to work with. I know it's not a trivial topic, but we are working on trying to move things in the right direction and improve the material quality and make this available to users easily. So simulations are about more than just estimating reverb time in diffuse conditions. Simulations can give far greater insights. One can visualize and analyze results. One can, of course, do oralizations as well, and so on. And non-diffuse conditions will be very common. I can also mention that ceiling absorbers will have different air cavity depths or different construction configurations than exactly what matches in a data sheet, which can greatly impact the absorption properties. The lack of phase information means that speaker interference, for example, cannot be accurately modeled. Oralizations will not be as representative as possible. So overall, we would like the uncertainty to go down and to capture phase, to capture these detailed properties in our simulations as well. That will make the simulations more accurate and more useful. And that's exactly what we are working to solve. So the Treble simulation engine can leverage impedance instead of only absorption coefficients when characterizing surfaces. Impedance is a far better measure or characterization of a surface because it captures both absorption and phase, and because it is a more direct physical characterization of the surface or the material. In other words, it's a more deterministic measure. You will get the same impedance results if you measure the material in different labs, as an example. So it's a better way to characterize the surface, but the challenge has been that this data has not been available or readily available, and furthermore, maybe it's not as intuitive to work with. So we want to try to overcome those two challenges. The way we approach this is that we will have a product hub or a product database in the Treble web app where material manufacturers can feature their products inside the hub, and they are then directly accessible to users. And behind every product, there are detailed intrinsic material properties, so one can be sure that you're using high quality data in the simulations. And we've been spearheading this with a few great material manufacturers that we see here on the screen. If we dive a little bit deeper into the methods we are considering here, then what we will do is that manufacturers will measure either the flow resistivity or the 6 J-cal parameters of the material in question. We're starting focusing on porous materials here. From this, we can estimate the impedance at all incidence angles. We can combine the porous layer with, we can either have several different porous layers or an air cavity as well with custom depth, and we can calculate the impedance of the whole construction using the transfer matrix method. And this means that users can simulate with high quality data and have custom ODS. For example, if we consider a typical suspended ceiling, as we see here, the manufacturer will have measured the flow resistivity or the J-cal parameters of this material here. The user will input the air cavity depth, and then we'll construct the impedance of this whole construction. We will do some clever things to account for the angle dependence of the surface, where we take, for example, the relative position of the source to the surface into account. And this will then be sort of all made possible in a very intuitive and seamless user experience for the end user. You don't need to be an expert in impedance or anything like that to work with this. An important partner of Treble in this process as well is, beyond the great manufacturers we mentioned earlier, is Matelis research lab. So manufacturers will be able to go to them to measure these material data if they like, or if the manufacturers have measured this themselves, then Matelis will sort of certify the measurements or the data sheets to make sure that that all data that is featured in the product hub is up to standard. So we're really excited about this. This is still ongoing work. We're still fine-tuning the methods. We're still developing the user experience and so on, but we've come far. We will also thoroughly validate this, of course, and share such results with the community. But I will now give the word over to Oliver, who will sort of quickly show how this will look and feel inside the product itself and the user experience.
Thank you, Finnur. I'm Ólafur, the product manager of the web application, and I'm going to show you the product hub within the web app. This is the place within the app where material manufacturers will have their own brand page with all of their products that have been verified in it. And you can see here some of the companies we have already been in talks with, Ecophon, Impact and AquaArt. And I'm going to walk you briefly through the process. Note that these are just designs at this stage, so this might not fully represent the finalized version. But let's click here on Ecophon as an example. You will then be able to browse all of the product ranges from the company that you choose and see some description of each product range. If we take, for example, the Ecophon Master product range here, we can go even further and we can see all of the different master variations, A, B, D, E, and so on, dependent on the edge finish. Within this site here, if I choose one product in particular, Ecophone Master A, I can look at it in closer detail. I can read the description of the material, some of the intrinsic properties, for example, the sustainability rating and the material description. In the finalized version, I will also be able to look at the absorption graphs for different ODS versions, or configurations rather. But the main thing is that after I've browsed the products and I've decided that I want to run it in simulations, I can add it to my material library here. And after I've done that, I can now use it to simulate. And the most interesting part, or one of the most interesting parts, is that in here I can select the air cavity depth from some predefined ODS, or overall depth of system configurations. So be it 50 millimeters up to 800 millimeters, or I can input my own custom ODS. And this is enabled by the AFR or JCAL description and the transfer matrix method that Finnur mentioned earlier, and really enables more robust and accurate simulations. So this is the process in a nutshell, and we will go over it in more detail when we get closer to a release date next autumn. But I hope you find it interesting, and we're very excited to build upon it further.
Hi, my name is Nate Fletcher. I'm a technical director in AKRF's Acoustics, Noise, and Vibration Group. We're based here in New York City with offices throughout the East Coast of the US. I have had a pretty long-standing interest in room acoustics, dating back to my master's in acoustics days at the University of Edinburgh, where I did my master's thesis rather, studying room acoustics, modeling methods, and human perception of different modeling approaches, including wave-based methods. So I was really excited in the early 2020s when Treble emerged onto the market as one of the first, if not the first, room acoustics modeling platforms that used wave-based methods for their simulations. This has been a really exciting development for us as acoustical consultants. It's been particularly helpful to us, not only on the analysis side for us, but also on the deliverable side as we look for new and innovative ways to communicate concepts that are abstract or possibly not the clearest to clients for them to understand, and be able to make decisions that are well informed and make those decisions quickly in some cases. So that leads us actually really well into this project that I'll be talking about today, which was for a major technology client of ours. This client was in the process of preparing for an art opening at a gallery here in Manhattan in the Chelsea neighborhood. They had visited the space, and they were concerned that the space was not going to be conducive for large gatherings, which they were expecting at certain events punctuating their schedule, and also wouldn't be appropriate potentially for live music and DJs, which they were also expecting at some of these events. So they hired us to assist them with analyzing and evaluating the existing conditions of the gallery, and they also were relying on us for recommendations on how to proceed, how to treat the space effectively in a way that would meet their expectations for the end user's experience within the space. So this was a tall order for us, not just because of the all of the different components of the contract, as I mentioned already, but most importantly, from signed contract to art exhibit opening, we had a grand total of 6 weeks, which, as I'm sure some of you understand, is not the right amount of time, typically at least, for us to go from a contract to an end user's finished product. So this presented a challenge for us, and we knew we had to take a different approach than we might typically on a project with a more typical timeline. So we were immediately thinking about what our analysis process would look like, and perhaps more importantly, what our deliverable might look like for this. We knew pretty quickly that it was not going to be a long drawn-out report replete with background information and analysis on reverberation times and speech transmission index and acoustic capacity and things like that we might typically want to do for spaces like this. We knew we had to get information to the client quickly. So in fact, simultaneously, we had some of our consultants out in the field doing the acoustical testing and working on the acoustical model itself, all at the same time in parallel. So by the time we had the data back in-house from our acoustical field testing, our reverberation time testing of the existing gallery space, we were already virtually ready to run the existing conditions model in Treble, which enabled us very quickly to calibrate the two to make sure our Treble model was aligning well with the field measured data. And then from there, we were able to iterate several acoustical designs based on feedback from the client as far as what they were looking for. Some of the challenges of this space included not only this compressed timeline, but also the fact that we really had no ability to provide any acoustic treatment on the walls because these were going to be used for displaying the artwork. We also knew that in addition to sort of the main gallery, there were multiple galleries off of that main gallery, and even those smaller galleries had coupled spaces off of them. So there were actually in total 5 spaces, all interconnected and coupled with one another, which were contributing to the various acoustic profiles of each of those individual spaces. So it wasn't it didn't seem appropriate simply to do reverberation time calculations, especially because the client really wanted to know how the space would sound in the different acoustical design conditions. And that's where Treble became an invaluable resource for us as consultants, not just in the analysis of what was the right approach for the client that we told them was the right approach, but for them to be able to experience the different acoustical designs and make a really informed decision. So at this point, let's jump into the acoustical model itself. We're going to look at the different acoustical design conditions and some of the geometries, and then have a listen to the different acoustical designs. So as you can see in the model, there are the 3 main galleries sort of in the foreground here, where you can see the sources and receivers set up. These galleries, and actually all of the spaces, were characterized by polished concrete floors, gypsum board walls, metal deck ceilings, and some glass skylights. So as you can see in the existing conditions, virtually no acoustic absorption whatsoever within the space. So we evaluated, we were only able to evaluate different acoustic treatments to the ceiling plane because there were no other options for us to finish with acoustically absorptive treatment. So we looked at a cloud option where we looked at 2 different, we looked at 2x4 clouds suspended 4 feet apart from the steel joists supporting the metal deck. And one of the advantages of this option was the client actually had an in-house carpentry team, and we were looking potentially, depending on lead times for prefabricated acoustic panels, looking at having them fabricate these panels themselves in-house. And we had provided some specs on how to do that. And then finally, we looked also at a full extent acoustic treatment finishing the metal deck ceiling itself. So as you can see, the 3 galleries are interconnected. There's sort of this barrier separating or subdividing the main gallery into 2 smaller galleries. This larger space is where the live band would be set up. And you can see already that we set it up such that we would have multiple conversations occurring simultaneously in each of the galleries. And then source 4 here is representing a DJ or a live band. And then off of the two smaller galleries were additional coupled spaces that, again, just added to some of the complexity of the acoustic profile of the space. So now let's go into the model and auralization itself. Here we are in the main gallery, in the existing conditions, and let's have a listen. So in this space, you can hear some reverberant energy, you can hear the live band, you can hear multiple conversations occurring simultaneously. And then let's go through the different acoustical designs. First with the 2x4 clouds. Next with the full surface acoustic treatment. And then back to the existing conditions, and let's travel around to some other locations within this main gallery. And then into the adjacent gallery. And hear how the acoustic designs change the experience within the space.
Il fera peut-être un peu froid, qu'on aura peut-être un peu de pluie, mais ils s'y attendent. Donc, et ils vivent en Angleterre, donc ils ont l'habitude de.
And finally into the last gallery, the one most isolated from the main.
Share their experiences and help each other navigate life.
So existing conditions,
With nothing to gain but the satisfaction of what they
clouds,
These acts of kindness
and full extent
remind
acoustic
us
treatment.
deep down, there's a wellspring of compassion within humanity.
So the advantage of this was that in a very short period of time, within a day or two of our existing conditions acoustical testing, we were able to send to our client acoustic renderings or auralizations of the space in its existing condition for reference, which they had already experienced, as well as a couple of different acoustical design conditions for them to evaluate. So instead of waiting until a full report was developed, QA/QC'd, and so on, we were able to iterate a couple of acoustical designs with the same technical rigor and quality control that we would expect of any other of our deliverables, provide that to the client, and they were able to make extremely informed decisions in a very short period of time so that they were able to meet the very compressed schedule that they had. The client was extremely pleased with the outcome of this, not just in terms of what the space sounded like in the end, but they were really grateful for the fact that we were able to communicate with such clarity how the different acoustic designs would be experienced and respond to their extremely compressed timeline. Simultaneously, we were grateful for the opportunity not just to provide a sort of subjective quasi-experience for them to hear, but one that was ground in data, that was extremely rigorous, connected to what we expect of ourselves as acoustical consultants in the treble modeling and analysis that we did. This has really transformed how we've communicated with our clients, especially on room acoustics projects, of course, and we're extremely excited to see how Treble will continue to improve our work, our analysis, our deliverables as acoustical consultants in the years to come.
All right, thank you, Nathaniel, for that great presentation. That concludes the kind of formal presentation part of the webinar, but we now go into the Q&A section, so please submit your questions below. Let's dig in.